So I want to talk about how we can demonstrate Newton's first law, that objects in motion tend to stay in motion and objects at rest tend to stay at rest. And when you say it like that, it really implies that there's not much of a difference between in motion and at rest. And this little cart here is going to show us how that's true. It shoots a ball straight up in the air. So we're first going to watch it do that while the cart is at rest. And then we're going to watch it undergoing various motions. And we'll try to explain why the ball behaves as it does. You can see at this cart, if the ball were to come right back down on the cart, it could re-catch the ball. And in some cases it'll be able to, and in other cases it won't be. So I'm back with our constant velocity vehicle, and I've got it hooked up with a tow rope, and it's towing this interesting cart, which is capable of launching a ball straight up. So what I want to do is I want to repeat that experiment, except I'm going to have the constant velocity vehicle tow the cart to the right. And I'm going to have the pin tied to this gas jet. So when the slack goes out of this rope here, it's going to pull the pin. And I want you to predict, if the cart is moving at constant velocity, is the ball going to land in the hole like it did, or is it going to land somewhere else? So give me a minute just to reset the cart. So ball down, pin in, should be ready to go. So we'll turn our constant velocity vehicle on. So I want you to see if you can explain why that happened. I put this picture together a number of years ago to explain what you just saw. Instead of having a launcher, we have a person standing in a school bus. And in this case, the school bus, the person, and the ball they're dropping all have the same initial speed. And as we saw from the old PSSC frames of reference video, if the observer moves along with this person, from their perspective, the person might as well be at rest. The person could drop the ball, it will land directly under them because the person, the bus, and the ball all have exactly the same motion, and there's no acceleration to change that motion. Check out what happens when you have an acceleration, which would be the equivalent of this bus speeding up. I have a hanging weight, and that hanging weight is going to pull the cart with a constant acceleration as soon as I take this book out. The pin's still going to be pulled by the gas jet, and I'd like you to predict, if the cart now has a constant acceleration instead of a constant velocity, where is the ball going to land? So here we go. So what happened there? Well, this would be like if the school bus was accelerating. And at the beginning, the person and the bus and the ball were all accelerating. And the ball was being accelerated by the person holding it in his hand. But the minute he dropped it, there was nothing accelerating the ball forward anymore. There was no force pushing it forward. The bus's engine wasn't connected to the ball anymore. So then the ball fell straight down, and the bus and the person continued to accelerate. And that would make the ball fall behind them. That's why you saw the ball fall behind on the cart that you were watching. The opposite would happen if everybody was going in one direction and all of a sudden we had a backwards acceleration. This would be the equivalent of the bus braking, and I didn't manage to demonstrate that with the classroom toy. If at the beginning the person and the ball and the bus were all slowing down, in other words an acceleration backwards from their velocity, the minute the person lets go of the ball, they're no longer pulling on the ball. So the ball's an object in motion, it stays in motion. And if the bus had been going at constant speed, the person would be here and the ball would have fallen straight down. But once they let go, the backward pull on the person and the bus meant that the ball appeared to go forward.